Welcome geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
So in this question, we are given the extension versus force graph. You're supposed to mark with a letter L, where beyond which Hooke's law does not apply. So you must mark the letter L at the end of the straight line. Now then let's state how the spring constant may be obtained. Now we know that the spring constant is supposed to be ratio of force to extension. But then our graph is extension versus force. So in order to get the K, you have to find the gradient first, alright, which is x over f, and then inverse it. So we call it the reciprocal of the gradient. So you can write down here, it is the reciprocal, that means 1 over the gradient of the graph. Then the copper wire is fixed at one end here and passes over a pulley, and the mass hangs here. Now the length is given as 2.5 meters and the mass is increased by 6 kg. So we're going to add a 6 kg mass, and the pointer then rotates to an angle of 6.5 degrees. Now the pulley diameter 3 cm is rough so that the wire does not slide over it. Show that the wire extends by 0.17 meters. Now because the pulley is rough, when you hang the additional mass and the wire stretches, it will cause the pulley to rotate. That's why you need the pulley to be rough. So in order to find the extension, right, we can assume that the extension will be the length of the arc traveled by the pointer. So let's say the pointer is here and it rotates over to here, then the length of the arc would have been the extension of the wire. So what is the formula for the length of the arc? If you are using in radians, then it's s equals to r theta. Then you convert the 6.5 degrees to radian by dividing by 180 degrees and times pi. Then you'll be able to get 0.17 centimeters. Now the other alternative is to keep your angle in degrees, but you have to use ratio. Since 360 degrees is 2 pi r, so 6.5 degrees will be 6.5 over 360 times 2 pi r, and then you'll also get 0.17 centimeters. Since they gave us the original length, which is 2.5 meters, and they asked us to calculate the increase in strain, so remember, you already know the extension caused by the extra 6 kg, so we call that extension, the extra extension. So why we call it extra extension? Because remember, they already said there was a mass there. Alright, and when the mass is increased by 6 kg. So this 0.17 centimeters that we calculated earlier is due to the additional 6 kg, not due to the total mass. So this is the extra extension over the original length. So that is the extra or the increase in strain. So the next part, they give you the cross-sectional area. They ask you to calculate the increase in stress. So remember the 6 kg that you added is an additional mass on top of the original mass. So this is the extra force. So the extra force over the area, cross-sectional area, gives you increase in stress. So then you're supposed to use the two values to calculate the Young modulus. So basically they're asking you to use the increase in stress and the increase in strain from the previous part to calculate the Young modulus. But let me explain to you why this is accepted, or why this is okay to do. Because remember, when we define Young modulus, we're supposed to define it as ratio of stress to strain. So ratio means you must take a single point. For example, if you have a stress versus strain graph, on a straight line through the origin, you're supposed to take any point here. So you take that stress over that strain. So how come this time I can find the gradient? Because I mentioned to you before, if it is a straight line through the origin, we can either take the ratio of the value of stress and strain at a single point, or we can find the gradient. You'll get the same answer, right? So what we did was we found delta stress, which is change in stress or increase in stress over increase in strain, which is actually the gradient. That's why it is possible to get the answer. So remember, this Young modulus of copper is what, 10 to the power 11. So all these values you need to memorize. Like for example, steel is stiffer, so that will be 10 to the power 12. So you must roughly know what are the values. Right, how would you check that the elastic limit is not exceeded when you add the extra load? So remember, elastic limit is the point beyond which your material will suffer permanent deformation. That means it will not return back to your original length. So that's what we need to do. So we can tell them remove the load or remove the extra load and check if the pointer returns to its original position. Because if it returns to its original position, that means it is still within the elastic limit. Now for this question, they give you the extension and the force, and then what they told you was you're using the same material, half the diameter and quarter of the original length. Alright, stretch for the same load. What is the extension? So for questions like this, we would actually use the formula for Young modulus, because same material implies the same Young modulus, and we are using the same load, so same F, but the diameter which will affect the cross-sectional area and the length is changed, so we know that this is a ratio question. So the formula for Young modulus was FL over AX, but we are going to change the A to pi over 4d squared. Alright, so why we do that? Because the question is in terms of diameter. Okay, then we finish it up by putting the x there. Now, since we want to find extension, we're going to make extension as a subject. So it will be FL over pi over 4d squared times E. So what are the quantities which are constant? Same material means same Young modulus. Pi over 4 is a constant. Same load, F is constant. So the only two variables are the length and the diameter. So what we can do is we use the ratio x2 over x1 equals to L2 over D2 squared divided by L1 over D1 squared. So group the L together, group the D together. Alright, so since the length is quarter and the diameter is halved, so this will be halved. D2 is the one that is halved. So don't forget to square it. So you get 1 over 4 times 4. So the answer is 1. So basically the x2 will be equals to your x1, which is the same as your 8 mm. So the answer will be 8 mm. A sample of material, right? They give you the strain versus stress graph. And they did mention also that you're going to load it until it breaks. So this is your maximum stress where you can take before breaking. So we can call this the breaking stress, or also the ultimate tensile stress, because it's the higher stress. Now, to determine the Young modulus, I always say that you've got to find the ratio of stress to strain at any point. So let's say I take the last point here, the breaking point. So where the stress is 9.5 times 10 to the power 8 and the strain is 0.013. So I take the stress divided by strain, I'll be able to get the Young modulus. Now, then they told you a second cylindrical rod of the same material, so that means we can use back the same Young modulus if we want to. Alright, is given here. Now, they give you the cross-sectional area and the force that is being applied. So, calculate the maximum area of the cross-section of the bubble such that the rod does not break. So, actually, there's a bubble inside here, which is actually an air bubble. So, what is the maximum area of the air bubble that you can allow? Now, in order to understand these questions, I want to illustrate to you an experience that I had while I was working in a die casting factory, where they would actually make metal parts by melting the metal and injecting it into a shape or a cavity. Then when the metal cools down, then you get the shape. So the thing is, every time you inject the molten metal into the die, right, the shape that we want, the empty cavity, so you'll notice that as the molten metal flows in, it also carries with it some air. And so what happens is there will be some air bubble trapped inside the material. Now, the problem with having the air bubble is it makes the material hollow here. So if you were to allow a bubble to be too big, that means it will weaken the material to the point that it will break easily. So therefore, we will never allow the bubble to be too big. So like in this case here, what is the maximum area of the bubble that they can allow? So to calculate this, we need to use the formula for the ultimate tensor stress, which is the maximum stress that you can take before breaking. So that one we obtained from the graph. Remember, the highest stress that we so happen to use it to find the Young modulus was 9.5 times 10 to the power 8. So this is the highest stress that the material can take. Then you're applying this force, so we substitute this force here. Then you will be able to calculate the area. But what kind of area are we calculating? We are actually calculating the minimum area of the material that we need. So why I say minimum? Because your stress is inversely proportional to your area. When this is maximum, this is minimum. So this is the minimum area that you need in order to prevent your stress from exceeding this value. Because if the area is smaller, then this stress will be bigger and will break. So 2 times 10 to the 6 is what we need. So if you notice that the area here is 3.2 times 10 to the power -6. Now, when you're making any part, like for example, in my experience in the factory, they would make the parts slightly bigger, alright, bigger than what you actually need, because they must allow space for air bubbles to form, and so that we don't have to reject every single part. So in this case, they made it 3.2 times 10 to the power -6, but the area that we need is only 2. So why am I make it extra? Because the difference here, which is 3.2 minus 2 times 10 to the power -6, is actually the extra area that you can allow for the air bubble to form. So you subtract these two, and then you get this area, which is the maximum area that you can allow the air bubble. And for the last part of the question, they give you a straight rod of the same material is bent. So why will a thin rod be able to bend more than a thick rod without breaking? So imagine that this is the thin rod that they gave you. The thick rod I'm drawing on top of the thin rod. So I'm going to bend the thick rod over the same angle as the thin rod. So you will notice something. If I were to extend this line here, joining the edges, it will be something like a arc of a circle. So if you remember, the formula for the arc of a circle S here equals to R times theta. So you will notice that the bottom of the thin rod and the bottom of the thick rod, I made them overlap. So basically the bottom part are the same for the thin and the thick rod, but the top part of the thick rod and the top part of the thin rod is different. So therefore, if you are finding the length of the arc here, you would have to take S equals to R times the theta. And for the length of the arc for the thin rod, you will use the same formula, but the R will be smaller and the theta is the same. So when R is smaller, S is smaller. So in other words, this thin rod has a smaller extension at the top compared to the thick rod. So the thick rod experiences a larger extension, so therefore it experiences a larger stress, and therefore it will break first. Right? So can you write down there? So you see, for the same angle that the thin rod is bent, the thick rod will experience a greater extension at the top. Therefore, it will experience a larger stress and it will break first.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with 1 or 2 past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.